It was very good. Okay, I see you're recording. And okay, so what I'm gonna present here is the work of myself, my group at TU Delft, and colleagues at INCAR and other places in the US, and also Dutch collaborators at IMAU in Utrecht. Okay, so this figure is about the mass evolution of the Greenland ice sheet in the last couple of decades. So the current contribution is around 0.7 millimeters per year, record mass loss in 2019. And if you go through the last IPCC report, you will see that most of the projections are focused on the century scale, and they are performed for Greenland, and they are performed with ice sheet models that use SMB forcing, so surface mass balance forcing from regional climate models. Okay, so then the modeling combination by default is this ice sheet model plus a regional climate model that provides the surface mass balance. But in this case, we are missing the coupling with the global climate. No, we don't do it all together within the same framework. Okay, so the question I'm gonna be addressing here is how fast will the ice sheet melt under different scenarios of greenhouse gas forcing in the future. And I'm going to address this question with coupling between the ice elevation, ice dynamics, surface mass balance, and the global climate. This coupling is relatively rare, so it is still developing for many climate modeling centers because it is challenging. So the number one challenge possibly is related to resolution, both spatial and temporal. So the standard climate model that is used in IPCC assessments doesn't have enough resolution to solve the large melt gradients at the margins of the ice sheets. And also we have time issues because these climate models are very expensive, and we cannot afford running them for very large periods of time. And ice sheets typically they need these large periods of time. They have a different time scale than the atmosphere. Okay, another challenge is how to initialize these coupled models, because we need to initialize the climate model together with the ice sheet model, and running a climate model for a long period of time is very difficult, very expensive. So, okay, so the community system model has been addressing some of these big challenges in coupling ice sheet and climate models. And it was the first GCM to simulate a realistic surface mass balance. So here you have a figure from this publication when the simulation by the community system model version 1 was compared with a regional climate model, RACMO 2 at 11 kilometers. So the climate model was running at 1 degree, and through elevation classes, the product of the SMB product was downscaled to this 5 kilometer resolution so that it could be used eventually by an ice sheet model. Okay, and so moving to the version 2 of the community system model, now we have a bidirectional coupling. So it is not only the SMB that is simulated interactively with the climate, but also the ice flow is coupled. So this is this has provided a first coupled simulation of the Greenland ice sheet that has realistic SMB, and that can also simulate realistically the ice discharge within an air system model. Okay, so what we are gonna see today is a little bit of model description, and also results, scientific results. There are two categories in the presentation. One is for simulations where we have coupling between the SMB and the climate, but the topography of Greenland is kept fixed to present day. And in the second block, I'm gonna be presenting the couple model where the icy topography can evolve. We have icy dynamics. Okay, so I'm gonna start with SMB, and I'm gonna explain a little bit the concept of elevation classes. So what we do in the model is we are calculating the surface fluxes of energy and mass. Sorry. Okay, I don't know if you can hear me still. Yes, okay. So yeah, so what we do is we are calculating the fluxes at several fixed elevations, and this is to capture the subgrid variations in the surface mass balance that are related to changes in elevation. So we will recalculate albedo and all of the fluxes at different fixed elevations, and then we will be producing a weighted average of between these different elevation classes for each grid cell that the climate model has a 1 degree resolution. Okay, so this is how these different categories are represented. If anybody has like clarification questions, please feel free to interrupt me. And if it is a more long question like discussion type, I ask you please to leave it for the end. Okay, so here in this publication, what Raymond Selefol was doing, he was comparing how different fluxes would depend on elevation, on surface elevation in the community system model, and how they do in a regional climate model. In this case, it is RACMO. So we are comparing this downscaling that we are doing with the elevation classes with the dynamical downscaling that is done in RACMO. And altogether, the gradients of the variables where I don't know here now. So for instance, this is the variation of the SMB with elevation, and we have this 369 millimeter per year per kilometer for RACMO, and the comparison with what we get with CESM is quite good. But you can go variable by variable, and you will see some differences, discrepancies. Okay, so now moving to the evaluation of the surface mass balance. Here in this publication, we have an evaluation of the SMB and the Greenland climate for CESM2. So there is comparison with observations. This is comparison with reanalysis, comparison with regional climate modeling, RACMO, again, 11 kilometers. And here is a comparison of the SMB as it is simulated by CESM2 and as it is simulated by RACMO. You can see these fine scale features that cannot be resolved here, but altogether there is a reasonable agreement. Okay, so main biases, so we are missing this high accumulation in the south east, for instance. Okay, and now some after the evaluation, so some results. So we apply the model, for instance, to study what is the effect of sea ice decrease on the surface mass balance of Greenland. And we did that for a decrease of sea ice within the present day climate. So the only signal that we have is a reduction in sea ice that is depicted here for every month. So here you have, for instance, in September, this would be present day, and this is the reduction that is applied. No? So this is the sea ice margin. But the background climate is the same, it's a present day, so that we don't mix greenhouse gas signals with the sea ice reduction. No? So it's sea ice for our present day climate. Okay, so these reductions in sea ice produce this warming in winter, this warming in summer, a very different intensity of it, of course, because melt is happening in the summer, so then we don't have so much of this temperature increase here. And this is, we have the vertical, and we have zonal means here. Okay, so we see this warming here, and also this warming in the summer. For the SMB, so what we see is that the reduction in sea ice increases the surface mass balance in the winter. So because we have more precipitation, and it reduces the surface mass balance in the summer because we have more melt. And we have more melt because we have more of sensible and latent heat fluxes. This is the incoming third wave. We have opposite signs in the change here, and we have decreases in the albedo that make that the net incoming radiation is more with the sea ice decrease. Okay, and if we look at the summer circulation response, this is the change in blocking, this is the change in 5 kilometer geopotential height. And so here we have the average between 60 and 80 north, and we have degrees east. So here this is Greenland, no? That is. So what we see is this increase in the geopotential height over Greenland, particularly in the western part of it, and the temperature change also is more concentrated, particularly in height in the western part of Greenland. So we have higher pressure with the sea ice decrease, more warming, and we have warming, sorry, because there is no greenhouse gas warming as forcing here. Okay, so now we move to a different simulation. Here we are increasing CO2 by 1% per year until we reach 4 times CO2. This is happening at year 140, and then we keep it at 4 times CO2. And when we take the last the decades between year 130 and year 150, 2 decades, and we compare with pre-industrial, so we get this warming in winter and summer, and these changes in the cloud fraction, changes in precipitation. So you can see increases in precipitation for part of in winter, for part of Greenland, and we see decreases here, and this is very much connected with the changes in the NAMOC, because the NAMOC weakens very much in this simulation, and it weakens very quickly. So this is reflected here. In the summer, what we see is increases in precipitation all over Greenland. This is how the SMB is in the control and how it is in this simulation of 150 years. I remind you that the CO2 is fixed here at 4 times CO2 at year 140. So a strong decline. We are crossing the 0 for the SMB, and the ablation area is expanding very much. So this is how the SMB looks like by the end of the simulation. This is the precipitation change that we have. Now it is annual means, and this is the snowfall change. So we have this reductions here and increases there in connection with the NAMOC weakening. And these are increases in melt and changes in refreezing. Okay, and so if we look at the time series, I want you to focus on the melt. So the melt is increasing as the CO2 is increasing, but at some point we see a very, very, very strong acceleration in the melt rates, and they increase very, very quickly, and this is coincidental with this large expansion of the ablation area. And okay, and we see the refreezing increasing as the melt is, but cannot catch up as a percentage of the total melt. And yeah, so we are here with the refreezing and not exceeding the amount of snowfall for the refreezing. Okay, the incoming short wave by the end of the simulation is less than in the control, in the pre-industrial control, and this is because Greenland is much more cloudy. The long wave incoming is increasing very much. The albedo is going down, yeah, as these ablation areas are expanding. And here you can see what happens with circulation, because this is a very big question for us. So how future circulation changes will affect the surface mass balance, as the recent melt extremes have been, for instance, the one in 2019, have been associated with particular circulation anomalies, so very strong blocking over Greenland. So let's see what the model says, or is projecting in this case for this scenario. So we look here at the summer. The model is projecting a more positive NAO and decreases in the blocking index. So it's going down, and this is probably, so this is inconsistent. Inconsistent or different than what we were seeing for the sea ice decrease. So the sea ice decrease was increasing the blocking, but that was without the greenhouse gas thing. It was only about the sea ice effect. And here we are having together the sea ice reductions, but also the overall warming, and also we are having the NAMOC weakening. And we believe that this reduction in blocking is related with the NAMOC change and associated climate impact. Okay, and for the jet doesn't change so much in position. Okay, so blocking going down with time, and NAO going up. Okay, and this is the correlation with the melt. So melt decreases with the NAO and increases with the Greenland blocking index. Therefore, we have melt decreases from the increase in the NAO, and we have melt decreases from the GBI decrease. So altogether, the projected circulation changes result in melt reductions. But please take this with a grain of salt, because it is just one scenario. It is for 4 times CO2. We have very, very strong NAMOC weakening, and we have very, very strong warming happening here. So more simulations are needed. Okay, so this is another study that is done only with with the interactive SMB, but prescribe ISET topography. And so here we were addressing this problem that most of the CMIP6 models, they don't include a calculation of Greenland melt. But we have quite some simulations of the community system model with this melt calculation. So we can train. So we came out, or Raymond Selefol came with the idea of training an artificial neural network with input of atmospheric variables of the community system model and the melt that was calculated by the community system model, and trying to use these patterns to obtain melt for the whole set of the CMIP6 models. So with that, we are performing a cheap, relatively inexpensive calculation of melt with the full CMIP6 archive. And this is something that we cannot achieve with dynamical downscaling that is being done with regional climate models, because it is very expensive. So we wanted to cover a little bit this gap. No? So we cannot downscale with all regional climate models. So let's try and see whether we could use a neural network for that. And so, okay, so this is for the training. When we did the training with CESM, yeah, we could use temperature and geopotential and clouds and so, and we would get melt. But then when we went and used the climate models, we found that these two variables, so 2 meter temperature and snow, would work the best. We evaluated with a regional climate model with MAR that was dynamically downscaling the very same set of GCMs in 5 or 6 simulations. And then, so we ran the thing, and this is what we get. So this is from the full CMIP6 archive. This is the global mean temperature change for several scenarios, and this is the range of melt that we project by using this. So it goes in between 1 millimeter. This is melt, so without considering refreezing. So it is not SMB, and it is not the full thing, including the ice dynamics. So from melt, it would be in between 1 millimeter and 4 millimeter sea level rise. Okay, so these are the conclusion. Sea ice reduction alone increases the blocking and warming over Greenland and increases the melt. For high warming, CESM is projecting that circulation changes reduce by themselves, no? Not anything else. They reduce the melt. And also we have this other study where we use temperature change and snowfall from the CMIP6 models, and we get a projection of melt. Okay, so now moving to the coupled work. So what we have in the coupled model, so the community system model coupled to the community ISET model, is an ISET model running at 4 kilometers, and an SMB calculation that is done at 1 degree, but with elevation classes, we can get the product at a 4 kilometer resolution as well. And then we can provide ice discharge to the ocean model that is called POP, and also the runoff to the ISET model. And as the topography of the ISET is changing, this is communicated to the climate component. And as the area is changing, this is also communicated to the climate component. Okay, how do we initial? Oh, what? I don't know what happened here. I'm sorry. Okay, something went wrong with the Microsoft PowerPoint. I'm going to open again. It's a very large file, so maybe give some kind of problem. Okay. Again, no. Okay, so we're looking at the initialization. So we initialize the model starting with present-day topography of Greenland. And we ran semi-coupled the climate and the icing model for 10,000 years. But we were not always running the climate model for so long. 10,000 years is incredibly expensive. So we were switching moments where everything was coupled with offline forcing to the icing model, and then we would recouple. Okay, so what we obtained was a climate that was very similar to the CESM-2 alone, so without the interactive ICID. So we were happy with that there was no big perturbation in the system by the fact that we would turn an interactive ICID. And so in terms of ocean circulation, climate, everything was very similar. We have some differences that are mostly due to the fact that the simulated icy topography is not the same as the observations. No? And this introduces some differences in the climate locally in the area of Greenland. Okay, so we overestimate, so that our initial state overestimates volume. So this is our ICID, and this is the ICID from observations. But our ICID is stable. There is no major drift. We are happy, and we will work on a more realistic topography in future work. Okay, so results. So we apply this couple model to the period 1850 to 2100. So we have a historical scenario first, and then we change to SST5 8.5. And here is an evaluation of the ice discharge as it is simulated for this period 2000 to 2005. So these are observations, and this is what we get. So these are surface velocities, and this is per basin the observations and what we are simulating. So this evaluation is in this GRL paper, and also the results are in this GRL publication. So this is how CO2 is evolving in this scenario, and it is reaching more or less like 4 times CO2, 4 times pre-industrial CO2 by the end. So somehow we can compare some things with the idealized 4-time CO2 that we saw before. Okay, this is the Atlantic meridional overturning circulation, and it is declining very much. So these are spherups. So this is the historical evolution, and it is going down to 8 spherup here. And this is global mean temperature. So we have 5 kelvins of warming by the end of the century. And this is how the mass balance is evolving. So we are good here, close to 0 during the historical period, and at some point we start going down, contributing to sea level rise with Greenland melt. Okay, so in the present coupling, there is no ocean forcing to the outlet glaciers. So the ice discharge here is responding only to the change in the SMB. So as the SMB is melting the margins of the ice, then we have thinning, and then the ice discharge is less because the velocities will be less because of this thinning, and also the discharge is less because there is less ice getting to the ocean. So the response that we have in this simulation from the ice discharge is a continuous decrease. So it is decreasing. So we are not reproducing the trend, the present day trend of the present day increase in ice discharge. We are only simulating decreases because the SMB is going down. Okay, so we get I said, so here is the cumulative sea level rise by mid-century, and by end of the century is much more. So this is the sea level rise rate by mid-century, which is even below present day, possibly among other things, because we don't include the ocean forcing, and here we are at almost 3 millimeters per year. Okay, so we present an assessment per basin in the paper, and we compare the simulations with runs where we don't have the interactive Greenland ice set, and we find similar decline in the SMB, but the magnitude is not exactly the same because we are calculating things over different topographies, not the same as the observations when we are starting. So we get different numbers for the SMB because the SMB is very much coupled to the topography. For the NAMOC, we find a similar NAMOC decline. Okay. So let's look beyond 1 century now. So we go back to the 1% CO2 to 4 times, and we are going to look here at 3 centuries. So we are increasing CO2 here up to 4 times, and we are going to look at this period here at the time of stabilizing CO2, and then after 2 more centuries. So this is global mean temperature increase. No. The global is the thick one, and the one in the Arctic is almost double. So I think the Arctic amplification is something like 1.7, and this is the Greenland ice set temperature. So is the amplification is above. So it is not 1.7. So because this is a piece of land, and it has a permanent snow cover, so it doesn't give us as much amplification as the sea ice reductions in the Arctic give us, or the reduction in the snow cover over the Arctic land. Okay, so we don't have. It's not correct that we would use the Arctic amplification for the Greenland ice set amplification of warming. Okay, so this is the sea level rise. So we have more than 1 meter by year 350. So these are the rates, 2.2 at the time of stabilization here, and 6.6 millimeter per year here. Okay. Okay, so here again, we are plotting ablation area, and it's expanding. And if you look here at the melt, how it is evolving, so from year 120, we find a very high acceleration of the melt rates. And this is coincidental with this very rapid expansion of the ablation area. And if we look at the contributors to this melt energy, so what we see is that before this year, this threshold, or like breakpoint at year 120, most of the energy for the melt is provided by increases in the incoming long wave radiation. So it's increasing here as we have increases in the CO2 and the global warming is progressing. We don't get much of energy from solar at the beginning in the first century, because we have compensation of a slowly decreasing albedo and a decreasing incoming solar from the increased cloudiness that we have over Greenland. But when the ablation areas expand very much, then we have as primary contributor to the melt the net solar because of the albedo feedback. So from year 120, the big contributor to the melt is the albedo feedback. And also the latent and sensible fluxes here, they increase very much with this in connection with this expansion of the ablation areas. Okay, so this is how the albedo is evolving as this is summer albedo, and you can see here the imprint from the expansion of the ablation area. Okay. And here you can see how these sensible and latent heat fluxes are evolving. So this is the sensible in the control, and this is how it is changing by after 1 century, and after 3 centuries. This is the sensible, and this is the latent. So things are progressing. Okay, let's continue after year 350 and see what happens in the long term. So here we need to save some simulation time. And so what we do is from year 500, we are gonna run 5 years of the ICEN model with the forcing of 1 year of the climate model. So we assume that the climate is not changing so fast. So we can repeat the same climate or the same SMB. We can provide it to the ICEN model for 5 years, and then we recouple. And again, we are applying this 1:5 ratio decoupling between the climate model and the ICEN model. And so if you look here at the evolution of the SMB, that is this yellow line. So first it is positive and it is going down. This is the mass balance that is also including the ice discharge that is going down. And so from year 500, you can see a change in the variability, but it's just because we are applying this trick of running the climate model every 5 years. Okay, so you can see that the Greenland after 300 years is becoming land terminating, so it's not discharging to the ocean anymore because it has reduced the area so much, and it is not in contact with the ocean. Okay, so this is sea level rise, and here we are at the top of what we can do. So which means that in less than 2 millennia, the ice sheet is gone. This is pretty fast, but it's also very high forcing. Okay, so full deglaciation after 1700 years. Okay, this is a simulation of the surface mass balance. In blue is positive, so the ablation area, and in red is the ablation area. And so by now, I believe something like 50% is ablation area. And we see retreat from all margins, although you can see that the southwest margin is particularly fast, and the southeast margin takes a little bit more time because there is very high accumulation going on there, and not so much. The ablation area is very narrow currently. Okay, so we lose the southern part by year 900 or so, and the ice is retreating to this area here of relatively high bedrock. And so here is this bedrock below sea level. Okay, at some point you saw that the blue disappears, so we have 100% ablation area. And here we have a very, very small ice cap that disappears. So, so this is the evolution of melt, and it is the red line. And it is a scale by area. So I don't give you gigatons because it will be misleading. So because the area is going down, so we divide here by area, and we get kilograms. So an average melt rate, and this is how it is evolving. You see like a pause here in the melt increase. So the melt is increasing all through the simulation, except here. And this is when the ice is retreating to this relatively high bedrock area. So then it is thinning, so it's becoming smaller, and it is losing the ablation areas that are at low elevation, and as it is moving to this area with high bedrock, then the surface elevation is relatively high, and then there is this apparent decrease, not decrease, but non-increase. So like this break, this pause in the melt increase. Okay. So if we look at the energy fluxes, so this is a continuation of the story that we saw before. So the latent and the sensible are providing quite some, particularly at the end when we have this very small ice cap. And the solar is giving, the albedo feedback is giving a lot of energy for melt. Okay, this is a simulation of the surface velocities, how they are evolving also. And I'm going to move to another study. It is not published. We are preparing a paper, and what we did here is we have the capability of running the icing model by itself with an SMB that includes a dependency with elevation that is coming from the elevation classes calculation. So we can run the icing model with a certain SMB. We can have some kind of elevation feedback, but we are freezing the climate because we are not doing a couple simulation. So so we are taking this 4 times CO2 simulation, and yeah, so it was running from year 0 to year 350, and we were taking the SMB corresponding to different periods. So periods when the transient warming was 3 Kelvin, 3.2, and 5.2, and also when it was 8.5 Kelvin here. So, and we repeat this forcing all over for the icing model, and we are looking to which ices will go and which ones will not. So this is the SMB, the initial SMB that will be corrected with elevation changes as the icing model is running. But this is the initial SMB that we have. So here is very, very negative, and up to this second color red, the SMB that we are giving is positive. And this is the standard deviation because we are taking 20 years of SMB. Okay, so what we are trying to find is for which of these simulations the ice sheet completely is completely gone, completely melts. As yeah, a first guess is that the ice sheet will be gone if the SMB is 0, of course, but this is a very conservative threshold for the ice sheet to go. So let's see what this model is taking. So when we run, this is our final states. So these are for these simulations with initial 352 gigatons per year, 313, and so so for this one, we are losing the southwest, and then it eventually is stable at this configuration. And then for more forcing, we have this splitting of the ice sheet, and it is for this one that the final volume is around 1 meter sea level equivalent. And this was our threshold to consider, okay, it is gone. The ice sheet is gone. So we find it for a positive SMB that is pretty high. So it's more than 200 gigatons per year. Okay, and of course for negative initial SMB, then we are losing the ice sheet as well, and very fast. So here is 7,000 years, and here is 2,000 years. Okay, so these green simulations are these two here. So the equilibrium ice sheet is has 4 meters sea level equivalent, and the yellow runs are these ones. And then the equilibrium after 40K, so 40,000, the equilibrium one is 1 meter, and we consider this is completely gone, or our threshold to think it is gone. So we have some separation here in between the simulations. Okay, and this is the SMB. So we are starting for all of these runs. Here we are starting with a positive SMB, and the SMB goes down, and in some cases it will be eventually still positive, but yeah, but here will be not enough to prevent the ice sheet to go. Okay, so this was uncoupled. We are writing up this, but at the same time, we want to look at this threshold for complete deglaciation of the ice sheet also in a coupled approach. So now running also the ice sheet model, we're going to apply the same thing of switching to 1-to-5 coupling after year 500. But we are going to try other scenarios that are less forcing than 4 times CO2. So these scenarios are, so the 4 times CO2 that we saw before is this red line. This is global mean temperature, how it is evolving. So this is pre-industrial, and how it is going up in the 4 times CO2. And this is how it goes in a 3 times CO2. So at the time that we are stabilizing at the 3 times CO2, the increase, the trend for the warming reduces, but still the warming continues because we have this inertia that is coming from the ocean for the warming. And this is for 2.5, the evolution of global mean temperature. These are years. From year 500, the ice sheet model has a different clock. These are climate years. So, and here we have 2 times CO2. And in 2 times CO2, there is some breaking of the rules because we see a first trend until stabilization of at 2 times CO2, a second trend, and then there is a third trend. So there is an acceleration in the warming, and this is coincidental with recovery of the NAMOC. So the NAMOC is declining very quickly and going to these bottom levels here for 2.5 and more. But for 2 times CO2, it goes this way, so more slowly declining and hitting the bottom and then recovering. So this increase in the global mean temperature of 1.5 Kelvin is coincidental with recovery of the NAMOC. And this GrIS simulation, in this one, what we did is we re-established pre-industrial CO2 over 2 decades. We increase it over 2 decades. And so the global mean temperature is going down, and the NAMOC has this overshoot, and then it slowly goes down towards what would be something like a pre-industrial level, hopefully. Well, hopefully, not hopefully. We think it will go there, but we didn't continue the simulation. Okay, so if we look at the pattern of the warming, this is annual, is post recovery of the NAMOC, before the recovery of the NAMOC. These are the temperature anomalies. So we see these are annual and this is summer. So we see warming over Greenland, not only in the annual mean, we also see it in the summer. So we think this is gonna affect the melt. And yes, these are time series of runoff given as SVEDRUP, so as input to the ocean model. And we see that after this recovery of the NAMOC, the fluxes from Greenland with the climate model clock, again, they increase. So a part of this will be because of feedbacks of elevation and so on, but another part is related to this warming that we can see over Greenland. Okay. So the conclusions and a little bit of an outlook. The couple, the CESM and CISM, compares relatively well with regional climate models and with observations within limitations. A main limitation is that the initial area and volume are overestimated. So we have 1 extra meter of sea level equivalent over Greenland. In the CO2, in the high high CO2 scenario that is provided by 1% to 4 times CO2, we see that the long wave increases provide most of the energy for the melt increases, but then the albedo feedback is kicking very strongly, and also the fluxes that are related to directly related to temperature, like the sensible and the latent heat fluxes. Okay, what I am putting in blue is the outlook. No, so I mentioned that the initial area and volume are overestimated. So then this is for the outlook for future work. Okay, in absence of the ocean forcing, the ice discharge is rapidly decreasing, but then the outlook is to revise these results by including ocean forcing and seeing how the SMB and the kick from the ocean come together. Okay, so we have an ice sheet lost in less than 2 millennia and therefore 4 times CO2. And in uncoupled simulations, we find a relatively large positive SMB threshold for total mass loss. We need to revise that with the coupled simulations that are in their way, no? So they are not finished, they have different lengths. And they don't go up to, I said, the glaciation. Okay, I think I if you with this slide maybe, and if you wanna start with questions, they are very welcome.
Thanks, Miren. That was fascinating talk. Do we? Oh, we have some clapping and other things going on. Patrick is clapping. Nice. So first up, we've got Letty's raising her hand, and then Jeff. Letty, would you like to go ahead and unmute for us, please?
Hi. Yes, I can. Can you hear me okay?
Yes.
Hi. Thank you for the talk. That was great. I wanted to ask a little bit more about the spin up. If you could just talk a little bit more about that and whether you have any thoughts about how you might reduce the expense of spin up going forward. And also if you make physics changes in the ice sheet model, what kind of plans you have for spin up after making those changes?
Okay. So I don't have the time series here about how things are evolving for the initialization. Okay, what is it? Okay, so if you go to this paper, then you can see the time series of how the volume of the Greenland ice sheet is evolving, and also the climate variables. No? But the final climate is relatively similar to CESM-2 only. So our thing is that we have an ice sheet that is 1 meter sea level equivalent bigger. Okay, so as we are coupling, the ice sheet primarily is adjusting to the SMB that is receiving from the climate model. So we have all this spin up of so we are spinning up the velocities at the same time that we are coupling to the SMB. So a way to reduce the spin up time would be to do some initialization of the velocities and with the SMB offline without recoupling with the climate. So then we don't have to run the climate model, and when there is some equilibrium, then recouple with the climate model. But now, yes, we want to include the ocean forcing, so we have to repeat the spin up. And yeah, so an idea would be that we provide the ocean forcing and the SMB forcing offline and equilibrate to the ice dynamics first, and then we couple together with the climate interactively. Yeah, that would be the idea to reduce time. Is there anything else that you need to know? Betty?
Yeah, sorry, thank you. Do you have a sense of what you might change for improving the ice area and volume overestimation?
Yes. So one thing is that the initial state for the ice sheet was prescribed. Was the present day ice sheet topography, and the thermal state, so the temperatures were coming from a spin up that was using the community ice sheet model 1, and that model was running with the shallow ice approximation. So then we have this transition of the basal conditions from what was produced with a shallow ice model to a higher order model as CESM-2. And so then you need some time to spin up the velocities. So yeah, so I would start with a different initial. Yeah, I would work also on the thermal spin up of the ice sheet model, and I would take it from the simulations of only the icing model that have been used for the SNP6. So yeah, so in a nutshell, I would start with span up velocities, and I would run first offline with SMB and ocean forcing, and then once this is calibrated, then couple with a climate model.
Okay, thank you.
Sorry, I was muted then for a second. Thank you, Letty. Next up, we have Jeff.
Hi, Miren. I presume you're not running here with isostatic rebound, which of course would slow the melting.
Can you repeat the question?
Are you running with isostatic rebound?
Yes, we are. Yes.
Because that would.
We are.
Because you still
Yes.
had the center. You still had the center of the ice sheets below sea level, whereas it actually rebounds above sea level.
I'm not sure if in that visualization the update of the bedrock was included. So maybe you don't see it because in the visualization it's not included, but we did include it in the simulation. And for the 4 times CO2 simulation, the glacial isostatic adjustment cannot catch up. So it can reduce a little bit. It reduces very, very, very mildly the melt rates because the melt goes so fast that, yeah, there's no time for that to happen. But we did these offline simulations to find the SMB threshold, these ones here. And in these ones, okay, we have 40,000 years, right? So here you see the simulation here, how the volume is going down. And it seems that the ice sheet is going to equilibrate here. And it is here for a while, and then boom, goes down. And then if we are running with the glacial isostatic, okay, and in this other one, we have some kind of oscillation. The oscillations come with the coupling with the glacial isostatic adjustment. If we don't run with glacial isostatic adjustment, the threshold is even higher. So I'm not sure, maybe the green one also goes. Because now we have a long time scales. So then the glacial, no, the other, yeah, right. So I think the green goes as well to this 1 meter only, if we don't include the glacial isostatic adjustment. So yeah, it makes an effect. It does.
I had another quick question. That it will be interesting to run these with emission-based scenarios rather than fixed CO2, because the CO2 drops off quite quickly from the emission ones due to the CO2 sinks, and so you get the ice sheet stops melting effectively at some point because you're getting down below a 1.5 threshold, 1.5 degree threshold, and so it'd be interesting using the RCP, which are emissions based, rather than the fixed CO2 ones you're using.
Yes, yeah. So this is an next step. Yes, definitely. Not only having this 8.5 there, extending the 8.5 and running other scenarios with overshoot. That would be very interesting. But the 4 times CO2 runs are very clean. So to start the running couple, this tell us it's very easy to separate things. When you control so much the forcing, you know that you are increasing the forcing up to some point, and then you don't increase it anymore. And so it was a first step, and then definitely it would be very interesting to run. Yeah. So one first step that we took is running the scenario where we reimpose pre-industrial CO2, and we will be looking at how long it takes to regenerate the snowpack, to regenerate the refreezing capacity, and yeah, to estimate the delays that come with yeah. As we cool, we also the SMB will need some time also to react.
Yeah. Okay, thanks.
Thank you, Jeff. Do we have any other questions? We are quite a bit over time here. We're about 10 minutes past, so we really should be closing out soon. But if anybody has any final questions or comments, it would be great to hear them now. Yeah, very quiet. There is some clapping. Okay. Okay. Seeing as we are quite a bit over time.
Yeah, I'm sorry for that. I wanted to stick to the 45 minutes and I didn't.
No, I'm sorry. It's my fault. I perhaps am too relaxed with him going over time. I assume it's okay, and it's nice to put the full material online, you know. And then I suppose if people want to leave, they can. So I hope people don't mind too much that we went a little bit over time. It's my fault. I will try and keep us under next time. But yeah, I just want to say a huge thank you to Miren again for a really interesting talk. And I hope you all have a great rest of the day.
Okay, thank you.
Thanks, everyone.